Hello, my people. I hope we're doing well today. These videos are for 3.10 in the Stewart book, which is linear approximation and differentials. And after having put up with about a week and a half of related rates, I'm sure that this will be a welcome reprieve from that sort of difficulty. Linear approximation is sort of a wonderful quick section to pair with 3.9 related rates. It gives us a nice little breather, and it gives us something besides related rates on the next test. But let's go ahead and dive right in. So you want to just sort of read along with me right here. So far, we have seen a couple of applications of the derivative, and we will see a lot more as we continue. But linear approximation is more of an application of find the equation of the tangent line to the curve problems that we've encountered than it is an application of the derivative itself. And so what we're going to start with is something along those lines and what I've usually referred to in the past as training wheel problems. So let's go ahead and get started with our equation of the tangent line problem. Let's say we're given f of x is equal to the square root of x. Now, of course, this should be child's play at this point. And we remember that in order to find the equation of a line, we need to find two things, point and the slope. Well, we already have the point, so let's go ahead and find the slope. That is x to the 1/2, so its derivative becomes 1/2 x to the negative 1/2, or 1 over 2 root x, which means that my slope at the point of tangency that I'm looking for, meaning at the point 4, 2, is going to be f prime of 4, which is 1 over 2 root 4, or 1 over 2 times 2, or simply 1 over 4, which means that our equation of the tangent line is y minus 2, so y minus y1, mx minus x1, and if I want to simplify into y-intercept form, which would be helpful if you were going to plug it into your calculator and graph it along with the original. It would be y is equal to 1/4 x plus 1. But if you're not going to use y-intercept form, you're more than welcome to leave it in point-slope form. That's why you learned that. It's a perfectly legitimate form of the equation of a line. Now let's go ahead and take a quick look at the graph of both of those. 4, 2 is this point right here. Okay. Now, because we have focused on slope so much, right, we should recognize that the slope of the curve is the same as the slope of the tangent line at the point of tangency, right? And we talked about how, a lot of times, especially those beginning problems where you find the equation of the tangent line, that's kind of the point, okay? But keep looking. You may also notice that near the point of tangency, the curve is almost indistinguishable from the tangent line, meaning that it's so close, the tangent line is so close to the curve that it actually looks like it might have very similar outputs. Now that actually becomes pretty handy, okay? That means that in terms of practical applications, that the tangent line becomes a very good means of approximating a point on the curve that is sufficiently close to the point of tangency. Now, the key word in all of that is sufficiently close, because if I want to use this tangent line to approximate points that are on the curve, it's not going to be a very good approximation over here at 8, but it is going to be a very good approximation here at like 4.5. Okay? So here's what we're going to do. We're going to use this tangent line to approximate the value of square root of 5. Okay? So if we want to approximate the value of square root of 5, we could use the tangent line for such an approximation, because the tangent line, as we said, was 4x plus 1. And of course, at 5, that winds up being 1/4 x plus 1. So the output for the tangent line, notice that that's a squiggly equal sign, so we're approximating f of 5 using the equation of the tangent line for its outputs instead of using the actual the actual function for its outputs. And I'm going to wind up with 5 fourths plus 1, or 9 fourths, which we know is 2.25. And I'm only putting it in terms of a decimal because we're actually going to look at how this number compares to the decimal approximation. And if you plug in root 5 into your calculator, it's of course an irrational number, but you will get a decimal approximation that looks something like that. Now, 2.236 is pretty stinking close to 2.25, okay? And if you actually wanted to, you could take this number, right, which is the actual, and you could subtract the approximation, again dividing by the actual, to give you a percentage error for how, and multiply it by 100 to get percent, right? And you would know at that point that basically our approximation has a percentage error of less than 1%, just a smidge more than 0.5%. That's a pretty good approximation, okay? Now, I said that the keywords were sufficiently close. Now, 5 is only 1 unit away from the input value for the tangent line, so it is sufficiently close. The next question is 6 sufficiently close? If I use the tangent line to approximate root 6, how good of an approximation is that going to be? Well, let's find out. We know that it's 1/4 times x plus 1. Well, 6 fourths is 3 halves. 3 halves plus 1 is going to be equal to 5 halves. And that gives us, of course, 2.5. Again, the only reason I'm putting it in terms of a decimal is so that we can compare it here in just a moment, because you know how I feel about decimals. Now, if you actually plug root 6 into your calculator, you get an approximate value of 2.449489,743. Now, that's pretty close, right? That looks like it's, 11, what is that? I'm not going to do that in my head right now. It's getting late. So let's just go ahead and use the same error, the percent error calculator, in order to find out exactly how good this approximation is. We're going to go ahead and basically take the actual, subtract the approximate, and divide it by the actual. 9,743, and what we're going to find out is that the approximate error is 2%. Okay, not bad, but certainly not great, right? It's not under 1%. It's not a fantastic approximation like root 5 was when you use the equation of the tangent line for that. Okay, well, let's keep traveling. Okay, let's actually look at root 7. And if we look at root 7, we may notice before we even get started that 7 as an input is closer to 9, right? So it's actually closer to the ordered pair for the function 9,3. And because of this, it might be better to use the tangent line at 9,3 because it would be, closer. So sufficiently close would be better satisfied by using the equation of the tangent line at 9,3 as opposed to 4,2. But to confirm our suspicions, let's do both. What do you say? Now, in order to find the approximation for root 7, we are again going to plug 7, or basically what it is we're trying to find the square root of, into the equation of the tangent line at 4,2. That is 7 fourths plus 1, or 11 fourths, which is 2.75. Okay. Now, if we actually look at root 7 and press enter into our calculator, we get 2.645751311. And again, we're kind of curious. Let's go ahead and see what the actual percent error is by taking the actual, or at least a darn good decimal approximation, subtracting the approximation and dividing by the actual again, and we can go ahead and multiply by 100, and what we're going to get is an error of 0.394 0. That's an error of almost 4%, okay? What that means is that the farther and farther you get away from 4.2, the worse and worse the approximation is going to be, which makes sense because you can actually see those two coming apart as the x values increase from 4 to 5 to 6 to 7 and on, okay? So what we're going to do at this point is let's go ahead and find the tangent line at 9.3 and see how much better of an approximate value we get there. Now, of course, we're still dealing with the same derivative because we're dealing with the same function. We're just dealing with it at a different point, and so we need to evaluate its derivative at a different point, and we get 1/6 as our slope, okay? Now, what that means is when you do y minus y1 is equal to m times x minus x1, we get that in point slope, and if you want to simplify, which in this case you should, we go ahead and get that in slope intercept. So let's go ahead and plug in 7 into this equation for this tangent line and see how good of an approximation it is coming from the equation of the tangent line anchored at 9.3 instead of the equation of the tangent line anchored at 4.2. And what we find is we get 1/6 times 7 plus 3/2. That's going to be basically, 7/6 plus 3/2, which is going to simplify to 16/6 or 8/3, which is approximately 2.667. So it's 2.6 repeated, okay? The actual, the better approximation from our calculator is 2.64 5751311. We saw that on the previous page. Let's go ahead and again plop it into our error calculator in order to determine how good of an approximation it really is. 2.64 5751311, and this is of course 2.6 repeated. And when I plug that in, I find that coming from the other direction, I get a much better approximation. It is back down below 1%, and so that whole basically comparing the equation of the tangent line at 4.2 to the one at 9.3 gives us a very good illustration of that concept of sufficiently close that I was talking about. Now, sufficiently close is dependent upon a particular function, right? And basically it's curvature. The more something curves, and if you think about it, the radical function that we're using, f of x is equal to the square root of x, actually starts to lay rather flat as x increases, right? And so tangent lines are going to lay against it really, really well, especially as you get to larger and larger x values. But compare that to, like, y is equal to sine x, which continues to oscillate, right? And the moment that you get even a little bit away from one of those values, sufficiently close is going to mean something different for a sinusoidal graph than it is for a radical function. So let's go ahead and put this idea of linear approximation to work by means of further examples. But before we do, and every book has a little bit different notation, you just have to be careful of what the notation means. This, for instance, is they actually give you the official, and use this for linearization but basically this is just the tangent line, okay? Basically, this right here is your y, this right here is your y1, this right here is your m, and this right here is your x minus x1, right? So it's basically just point slope with the y1 pushed over to the other side, and they're trying to doll it up and make it look really all fancy like it's a real formula, but it's something that you already know, okay? Sometimes A will refer to the value where the tangent line is anchored. Sometimes A will be the value that you're using in order to the approximation input instead of the tangent line input. So you just have to be careful and just have to basically go not upon a wooden understanding, a wooden sort of recollection of certain formulas, and you know how I feel about formulas, but basically based on what things mean, okay? So this is an example that I pulled from a textbook, and let's go ahead and take a look at it. It says, find the linear approximation L of x to f of x is equal to sine x, and so we're just going to jump right in to talking about a sinusoidal function near x is equal to 0. Well, that's actually not all that bad as long as you stay sufficiently close to 0, okay? So let's go ahead and we recognize the fact that f prime is going to be equal to cosine x, which of course f prime of 0 is cosine of 0, so that's 1. Now, of course, near x is equal to 0, that's just the x component. I need the ordered pair. Well, of course, if you plug 0 into f of x, you get sine of 0, so really it's basically means that the tangent line is the identity function, okay? Now, you could doll it all up and say, okay, well, L of x is equal to f of a plus f prime of a and x minus a, and then evaluate f of a as sine of 0, and then this as cosine of 0, and then x minus 0, but doesn't that just work out to x? I mean, so, you know, more than memorizing the formula, we just want to know what all these things mean, and that's infinitely more important, okay? So really what we're doing is here, let's go ahead and look at, let me get it so that it's not shining in any of these. Trying to get away from the glare. Okay, how about that? Okay, oh, that's actually nicer right there. Okay, turn off that for just a brief moment. So we have sine of x, right? And then we have y is equal to x, and those are our two graphs. Now, if we go to the window, let's go ahead and go from negative pi to pi, and then let's make the x scale pi over 6, and then let's go negative 2 to 2 sounds good for the y, because I mean it's the parent function of sine, so it's not going to oscillate beyond negative 1 to 1. And let's graph it, and we see, lo and behold, that we get one full period of the sine function, and here comes the tangent line at the origin, okay? Now, notice that sufficiently close, of course, means something different here, especially when it comes to this portion of the graph where it's going to start turning back away from, right? Where you have this maximum right here and it turns back and starts heading south again. But as long as we're close enough, it should be fine, right? Especially if you basically plug in values that are somewhere between this minimum right here and this maximum value, you're going to get values that, actually, let's just go ahead and change the window then. So how about negative pi over 2 and pi over 2, and that'll actually, let's go ahead and make it just make it easier to see. Go negative 1 to 1. And here's the sine graph. And so this is sort of half of a period. And here comes. So anywhere in this window, you're actually going to get a pretty decent approximation. So let's just do a few. I mean, they've given us 5 here to do, but we don't actually need to do all 5. That's, you know. So that was A. This winds up being B. Okay, well, it's really easy if you're using the identity function. So sine of negative 0.3 is approximately equal to negative 0.3. Okay, and if you're thinking to yourself, gosh, I wish I really knew what the actual value of sine of negative 0.3 is. So we'll do basically using the tangent line over here for the linear approximation, and I'll show you what it is in the calculator. 0.295520267. Okay, that, even despite the fact that it's actually not really close to 0, is still a pretty good approximation. Not bad at all, right? As we get into, say, sine of 1/2, obviously you get 1/2. And if you were to plug sine into your calculator, sine of 0.5 into your calculator, you would get 0.4794255,386. So, this was closer to this as this was to this, because as you get away from zero, as you get away from that point of tangency, you're going to wind up sort of diverging and getting a worse and worse and worse approximation. Again, the whole point is sufficiently close, okay? And if you wanted to graph it on your own, you just have to pick a reasonable scale. And let's do, how about 1 and 2, and this is pi over 2, and this is pi, and this is negative pi over 2, and this is negative pi. And so what we get here is something that looks like this for the sine graph. But of course, those are not on the same scale, right? And however, that pi over 3, which is right here, is going to be just a little bit more than 1. And so if you wanted to find 1, 1, you would just do it up here at 1, but just on this side of pi over 3. And this, of course, right here is 2 pi over 3. And so the same thing down here, you would do it just on this side right here, and then you just take a straight edge, and you can do it let's do it in a different color. What do you say? I like the idea of a different color. And we'll just we'll do it dashed as well. And I could have done that curve a little bit better because it definitely doesn't dip underneath that tangent line, but you get the idea. And that actually, it's good exercise to actually be forced to graph some of these things, because it does show you in a very visible way exactly how close they are at some points, and of course why they diverge and why values over here are not sufficiently close to the point of tangency to give you a good decimal approximation. Okay. Let's go ahead and let's flip over to the next page. Our next example comes from a different book that has a little different notation, right? A means something different here. So find the linear approximation of L of x to f of x. So find the tangent line to your original function at x naught, meaning that's the point of tangency. Previously it was A, but here they're actually using A as the value that you're approximating. So again, you just have to be careful not to think so woodenly about A always means this, and because in different books, according to different notational schemes, it can mean something different. Here they're using x naught for the point of tangency. In our book, the Stewart book, they use A for that. So let's go ahead and look at it. It says use it to approximate f of x at x of a. So basically what we're doing is this tells us right here that we need to find the equation of the tangent line. And of course when I plug 1 into here, 1 to the 2/3 is just 1. So let's go ahead and first find the f prime. So we get 2/3 x to the negative 1/3. And we know that we need to find the slope at that point. So we go ahead and plug in, and we find out that 1 to any power is going to be 1. So f prime of 1 is simply 2/3, which tells me that y minus y1 equals m. X minus x1 gives me that. Okay, and if I simplify it into slope-intercept form, I have to distribute the 2/3 and then add the 3/3 to the other side in adding the 1, and I'm going to get 2/3 x plus 1/3. Now, before we go any further, do you notice something about that graph? The graph of that is going to be even because that power is even, and it's only that one term, so it's in every term, okay? So we know that it's going to be even, so that's going to help us a little bit when it comes time for the graphing. But now that we have this tangent line, we want to know what f of 3/2 is approximately. F of 3/2 is approximately L of 3/2, and of course this right here is my L of x. That's my linearization. It's the fancy term for what you call a tangent line problem when you're using it for approximation. And so what we're going to do is we're going to plug 3/2 into here for x, and thankfully they've chosen a value that actually makes it really easy. 2/3 times 3/2, the 2's and the 3's cancel each other out, and that turns into 1 because it's 6/6. And so 1 plus 1/3 is equal to 4/3, and we should know that that's 1.3 repeated. If I actually plug it in and I look for f of 3/2, and I take that 3/2 and I raise it to the 2/3 power, what I get is approximately 1.310. And so the actual, when compared to the approximate, that's really not all that bad. Now, again, I want to go ahead and try and look at this. Now, the question is, of course, how to scale this. If we're going to scale this well, we need to take into account both of these, both this function and that. Well, that's got thirds in there. So why don't I just make it such that every 3 boxes is equal to 1 unit, and that's going to make the graphing a whole lot easier, okay? It goes through 1, 1. It goes through, I'm gonna need my calculator for some of these approximations. Now remember, and I hope that you do remember this, when I'm looking to get approximate values, I don't have to go to the main screen to do that every single time. Now sometimes your calculator freaks out a little bit, so if you plug in x to the 2/3 and your calculator freaks out, which sometimes it will, or maybe it's just mine, you can plug in x squared and then raise it to the 1/3, and it's the same thing, and sometimes your calculator basically handles that just a little bit better. You go over to the table format over here, and it's going to give you all of the inputs that you need. Now those are probably a little bit too small to see, but I wanted to show you that, and those are the values that I'm going to be using. At 2, you get 1.587. So 1.587 is going to be above 1.5, but not quite to 1 2/3, so it's going to be right there. And because this is even, it's going to have a symmetrical point over here. At 3, it's going to be a little more than 2, 2.0801. So right about there, and you're going to have the same thing over here. That means that this, I'm going to have to turn this so I can actually do a good job of graphing. So there we go. And that is our f, okay? Now, 2/3 x plus 1/3, we get 1/3 is your y-intercept, and then up 2 over 3, up 2 over 3, up 2 over 3, up 2 over 3, down 2 over 3, and I'm going to go ahead and use a different color again. And here is your linearization. That right there is your tangent line, L of x. Okay? And we can see that if we were to plug in right here at 3/2, right, that is where you're talking about. And on our graph, it actually looks almost indistinguishable, which is why the error right here is actually so good in terms of percentages. I'm going to go ahead and stop this first video right here. We'll get on to a couple of more, we'll get on to the rest of these problems in the next video. We'll do a couple more examples of linearization, and then we'll move on to the second topic in this section referred to as differentials.